All right, guys, welcome back. I want to start talking to you about our next set of family instruments and looking at chromatography. Now, in these upcoming PowerPoint presentations, I'm going to introduce you guys to a lot of material. I've put a lot of videos into these PowerPoint presentations to try to help clarify, because I know we're not meeting regularly face to face, so I've tried to introduce a lot of stuff into these PowerPoint presentations to help you guys out. So make sure you look at the PowerPoint presentations. Don't just watch the videos that I put up there, but look over the PowerPoints, watch the videos inside of the actual lectures, and that should help you out a lot. So let's get started here. And the first thing, um, so chromatology or chromatography is basically a group of methods for separating a mixture of substances into their individual components. And this, and even though this Russian botanist kind of coined the phrase chromatography, and that's pretty firmly established, we no longer really separate. And early scientists used to separate substances according to their colors. However, our modern techniques really don't use this to identify substances. Instead, we use what is called phases. And so this is all about separating mixtures into individual components. And so there's a few key terms I want you guys to be familiar with. One is the mobile phase. All right, so this is the gas or liquid that's going to carry that mixture through our instrument. Okay, and that's the stuff that we want to actually separate. All right, and then there's a stationary phase, and this is the part of the apparatus that doesn't move. All right, that our mobile phase will interact with. All right. Absorption, all right, is the adhesion of these molecules to either that gas or liquid to that stationary phase. We have solvents, we have solutes, we have the solution, and then the term affinity, which is just the natural attraction of force between things. So these are just a few terms I hope to help you guys out in their definition. And so in chromatography, we're basically dealing with two phases. Like I said, there's a stationary phase and a mobile phase. All right, and depending on the type of phase that we are using, all right, depends on the type of separation that we're doing. So separation of two or more compounds between, all right, these two stationary and mobile phases, right? And the two techniques that we're going to talk about, one is partitioning, and this is when we use a liquid to actually be our stationary phase. That's the phase that doesn't move, part of the apparatus. All right. And if we're using adsorption, all right, this is when we use a solid in that particular stationary phase. And then some of the applications, all right, for the different chromatography techniques, all right, we can apply these in biomedical engineering to medical or diagnosis, trying to diagnose different metabolites, vitamins, even looking at serum. Toxicology is a big one, all right, for looking at different types of drugs, especially in the medical industry, seeing if a person is overdosed on drugs. And forensic science is a big area, but we also use this a lot in research. There's also a lot of companies in South Carolina that are doing chromatography. So if this is something that interests you guys, I highly suggest looking into some of the companies around South Carolina. So a lot of different types of chromatography techniques. Again, like I said, the main areas of absorption and partitioning. All right, so in absorption, if we're using a solid phase, all right, we can also use, we can have gas interacting with that solid phase, or we can have that liquid interacting with that solid phase. All right, and in that liquid, all right, area, underneath that falls column chromatography, which we'll talk about, thin layer chromatography, and then the old school, which maybe some of you guys have some experience with, looking at paper chromatography. Again, if we're using a liquid stationary phase, we're going to call that partitioning. All right, but there's also a gas or a liquid as our as our mobile phase. And then in here we have column, paper, and thin layer. So depending on what combination of all four of these techniques depends on what we're going to actually use and what the application of this will actually be. All right, so paper chromatography is one of the simplest examples of chromatography, and this is an experiment that you may have often done in school. And typically you will place an ink spot, all right, near the edge of some filter paper and then hang it vertically with its lower edge near the spot of ink, all right, and dipped in some type of solvent such as like alcohol or water. And so then the capillary action, all right, will make the solvent travel up the paper, all right, where it meets the dissolved ink. And then, and so for paper chromatography, our mobile phase is that dissolved ink, all right, that slowly travels up the paper. And our stationary phase is the paper itself, all right, which is going to separate out the different colors or the different components of the ink. All right, and so this is a neat little example that shows that if I have all these different substances in which we added the color to separate it out, and we have an unknown substance, I can then compare it to what is likely. And here we're looking at different drugs. So thin layer chromatography is a variation of that paper chromatography, where the stationary phase, instead of being paper, is a vertical plate covered in some type of highly absorbent solid, such as crystals of silica or a silica gel here that you see here. All right, and the mobile phase is still some solvent such as alcohol or water. And the way this works is that if we have a substance that we want to separate into its individual components, right, we may introduce it into our system or place it onto our silica plate, all right, and then as that mobile phase then passes over this silica plate, it's going to carry with it that substance, all right. And then if we have two compounds in here, maybe this purple compound and this yellow compound, all right, as they begin to move through this mobile phase, they're going to interact with this silica surface, all right. And so if the compound has high polarity, all right, it's going to have a high affinity for this solid phase, all right. And so it's going to want to interact or stick to this silica surface, all right. And so it's going to move slower, all right, or not as far through the mobile phase, all right. If it has a low polarity, all right, or a high affinity for the mobile phase, it's going to want to interact not as much with the silica surface. It's going to want to stay more in the mobile phase, and so it's going to move further down the plate in the mobile phase. And so here we see our purple sample ends up not traveling as far. Our yellow compound ends up traveling much further. All right, and I can get a retention factor, all right, by which is a ratio that tells us how far the sample went compared to how far the actual solvent or the mobile phase where it ended. And this is and retention factors are useful for comparing results of one chromogram to another. And so if the conditions in which the chromogram were run were unchanged, meaning that we didn't change anything with the mobile or stationary phases, all right, the retention factor for a given material should remain constant. And so this allows us to look at unknowns and compare them to the known materials. And so if the retention factor of an unknown does not match that of a material that we ran, all right, then they're not the same compound. But if the retention factors are the same, then we can say that those two samples are the same. All right, column chromatography is one of the most popular forms of chromatography used in the industry. Hopefully you'll see why in a bit. The stationary phase is actually the column itself And there are many different types of columns out there. Some of them we'll talk about. One of the most common ones is a silica gel, but instead of being on a plate, that silica gel is now coated on the inside wall of the column. The mobile phase is a solvent or a mixture of solvents, sometimes called an elutant. And the way that it works is that you take your column containing the stationary phase and you load it with a mixture of our compound and the elutant at the top. And then as the mixture makes its way through the column, it splits into its individual components, which are going to travel at different speeds depending on their interactions between that mobile phase and the solid phase. The components then emerge one at a time, all right, at the end of the column, where we can either detect them or quantify them using a detector, or we can even collect them in individual like containers. And then usually the first spike that we see here in our volume is usually the elutant itself. So there's two types of column chromatography depending on what mobile phase we're actually using. There's gas chromatography if we're using a gas phase as our mobile phase. All right, and then depending on the type of column that we're using, we can have these three different types of techniques for gas chromatography. Liquid chromatography, probably one of the most popular ones. HPLC you might have heard of, high pressure liquid chromatography. All right, this is another column technique if we are using the liquid mobile phase. And then for that, there are several different types of liquid chromatography techniques that we'll talk about in the upcoming slides. All right, so now let's talk about gas chromatography. Gas chromatography utilizes a mobile gaseous phase that is absorbed onto the surface of a stationary solid phase. All right, mixtures are separated by taking advantage of the volatility of different compounds, or how easily those compounds will move from a liquid to a gas form. And depending on the boiling point of a compound, it will either have a high affinity for the mobile phase or a stationary solid phase. All right. And so if the compound has a low boiling point, all right, it easily stays in the gas phase and will therefore move quicker through the column. All right. And if it has a high boiling point, all right, it will not easily slip into that gas phase, causing it to interact more with the stationary phase and therefore move slower through the column. So this is the diagram of a typical gas chromatography instrument, all right, where we have a tank, all right, which contains the gas or mobile phase. This can be different gases, helium, argon, whatever. And then we have an injector where we inject our sample. All right, we have the column itself, which we see here as a bunch of coils, but that's just to increase the surface area. We also have an oven, all right, that's going to heat our mixture up and get that volatility, all right. And then we also have some type of a detector, all right, that's going to produce some chromatogram for us. And the way this works is at first we take a tiny sample of our mixture of substances that we want to study and place them in a syringe and inject them into the machine. All right, and then the components of the mixture are heated and instantly vaporized. Next, we're going to add that carrier, all right, or the elutant, which is simply some type of neutral gas, like I said, such as hydrogen or helium, designed to help the gas in our sample, or the gases in our sample, move through the column. In a lot of cases, the column is some type of thin glass or stainless steel tubing, usually filled with a liquid that has a high boiling point. But it can also be a gel or some absorbent solid. And so as the mixture then moves through the column, all right, it absorbs and separates into its individual components. All right, each component then is going to emerge or run through this detector at the end of the column and move past the detector, which this detector can sometimes actually be another instrument called a mass spectrometer or a mass spec, which can help identify and print out the peaks onto this chromatogram. All right, and then the final chart is just the series of peaks, all right, which will end up showing us all the substances that were in the mixture. Alright, so hopefully some of those videos helped out a little bit. But gas chromatography offers a number of important advantages in the analysis of these complex compounds. Alright, some of them are like the speed, the ability to operate with a small amount of sample, and like great sensitivity. Most of the instruments out there can complete an analysis um, of substances in like less than an hour, and even often in like 15 minutes or less. We really only need milliliter amounts of some sample to do an analysis with. And the sensitivity of these devices, even though they depend on the detector themselves, high quality instruments can detect like 1 nanogram quantities of a compound. However, there are some disadvantages to gas chromatography. One of the big ones is that it must be volatile, or samples must be volatile, which means they're not very good for looking at uh, molecules that we don't want to be in a gaseous form, right, in a vapor form, such as like biological molecules, proteins, DNA, things like that. Um, Oftentimes with serum and samples, uh, they're what we call dirty, right? So we have to do some type of purification to them in order to get them in a usable form, all right? And then often to do quantification of our samples, we have to use another instrument such as mass spec or something like that to actually get confirmation of our compounds. So some of the important applications of gas chromatography, obviously in human health, we can take serum, we can take urine analysis to look at different compounds found or perhaps identify drugs in the blood, things like that. In pharmaceuticals, right, being able to quantify drugs and the ingredients that go into those drugs, and then other areas such as cosmetics, environmental, uh, and inorganic, organic compounds, and things like that. All right, so next let's talk about liquid chromatography, or sometimes HPLC, high pressure liquid chromatography. There's several different types of this technique, and we'll talk about each one. So high performance or high pressure liquid chromatography is a very popular technique used to separate components and detect the individual components of a sample. Again, just a reminder, we're dealing with these two phases for separation and detection, and it's the interaction of the individual components with the stationary and the mobile phase that actually will separate the components. All right, so these are the basic components of HPLC, and flow through an HPL system is going to begin in the solvent reservoir here. And these solvent reservoirs contain the solvents used to carry the sample through the system. This is the mobile phase. And these solvents get filtered usually through an inlet solvent filter to remove any particles that could potentially damage our sensitive components of our instrument, and can be mixed to increase or decrease the polarity of that mobile phase. So bubble prevention is important because bubbles in a flow cell or a mass spectrometer source can interfere with the detection of sample components. And so therefore you'll often see a solvent degasser, which is used to prevent the formation of bubbles when mobile phase components are mixed into the system, and also a gradient valve or a back pressure regulator, which limits pressure drops along the flow path. All right. There's a high pressure pump which gives it that HPLC, high pressure liquid chromatography, and this pump propels the solvent through the system after they've gone through degassing. However, but because of the mechanical action of these pumps, we can still contain particulate material, so the solvent often passes through another inline solvent filter to prevent any post-pump damage. There's a sample injector. However, some more sophisticated machines might have like a switching valve that allows for automation of several samples. And these plugs of samples are injected using a syringe into the flow path. And samples can also contain particulate matter that can damage components. So therefore, a sample filter or a pre-column filter is often used to prevent valve or column damage. All right, and then next we have our analytical column, and this separates the sample into its various components. And samples are separated based on that differential affinity for the components, either in that solvent or in the packing material within the column, that stationary phase again. So after the analytical column, the separated components are then passed through a detector and are either collected or dumped into a waste reservoir. All right, and some of the detectors that we often see with HPLC are optical absorbance or UV, fluorescence, or mass spectrometry. In the next couple of slides, or next slide, there's a video I want you guys to watch that will also help explain some of the components of HPLC.
HPLC stands for High Performance Liquid Chromatography, but could equally well stand for High Pressure Liquid Chromatography. It is used for separating mixtures, either to analyze the mixture or to separate a required product from others in a reaction mixture. It can also be used to find the relative amounts of different components in a mixture. HPLC works on the same principle as paper chromatography, here shown speeded up. A liquid, called the mobile phase, moves past a solid, the stationary phase. In paper chromatography, this stationary phase consists of water molecules bound to the cellulose in the paper. The mobile phase carries different components of a mixture, called the sample, along with it at different rates. How fast each one moves depends on its relative affinity for the mobile and the stationary phases. For example, if the mobile phase is more polar than the stationary phase, the more polar components of a mixture will tend to move more quickly than the less polar ones. In HPLC, the stationary phase is a solid packed into a column, like one of these. This particular column contains silica particles to which C8 hydrocarbons are attached, making the stationary phase non-polar. In paper chromatography, the solvent moves along the paper by capillary reaction. In HPLC, the liquid is forced through the column by high-pressure pumps. The whole apparatus looks like this. These bottles contain solvents. Two solvents can be mixed in any proportions to give a mixture, the liquid phase, of suitable polarity for the separation that is being done. In this case, one solvent is water, very polar, and the other ethane nitrile, less polar. The operator can decide on a mixture with the correct polarity for the separation she is doing. These are the pumps. They produce a pressure of 15,000 kilopascals, 150 times that of the atmosphere, hence the name high-pressure liquid chromatography. If a single sample is to be run, it is injected into the solvent stream here, in the injection port, via a hypodermic syringe. Alternatively, several samples can be run in succession by loading them into this auto-sampler, which will run them in order without any human intervention. The pumps force the mixed solvents through the column. The solvent emerging from the column and carrying the separated components of the mixture passes into the detector. Here, a beam of ultraviolet light shines through it. This light is set at a wavelength that is absorbed by all the components to be separated. When the detector reading drops, a component that is absorbing UV light is coming out of the column and passing through the detector. Many alternative types of detector are possible. This one measures refractive index. The time that each component takes to come off the column is called its retention time and can be used to help identify it. Here, the HPLC instrument is being used to separate a mixture of two steroids used in a pharmaceutical preparation. The column chosen is packed with a nonpolar solid. The tails of the molecules represent hydrocarbon chains C8H17. Having chosen the solvents, detector wavelength and flow rate, a single sample is run by injecting about 20 microliters into the injection port. The more polar component comes off the column first, followed by the less polar. The peak at retention time, 1.5 minutes, represents other ingredients used in formulating the product. This is the pharmaceutical product, and behind it, its chromatogram.
So let's talk about some of the different types of liquid chromatography that we can see being used in the industry. And these different techniques are often dependent upon the actual material or how these columns that are used for the stationary phase are created. So the first one we're going to look at is the size exclusion chromatography, or SEC. This may also, in some of your textbooks, be called gel filtration. All right, and this is a technique that is often used to separate the different components of a sample by their molecular size. All right, and so a column will often be filled with these porous beads, sometimes like a silica or some other type of polymer, Cephadix, something like that. And these actual pores, all right, these porous beads will interact with the actual sample components as they pass through the column. And so when the sample passes through the column, all right, it's going to interact with these beads that are actually filled inside of the column themselves. And so depending upon the molecular size of the components, they will penetrate into these porous beads. And so the small components will penetrate further into the beads, all right, and spend more time interacting with the beads, and where the larger components will not. All right, so the larger components won't be able to infiltrate the beads, won't be able to interact with the beads as much, and so they will pass through the column quicker. All right, and so larger molecular size components will actually pass through the column quicker, and the smaller ones will pass through slower and have a longer retention time because they interact more with the actual gel beads themselves.
Separation in gel filtration chromatography is based on the differences in sizes from biomolecules as they pass through a column packed with a chromatographic medium, which is a gel. Molecules larger than the pores in the gel are unable to diffuse into the gel and are confined to the solution surrounding the beads. Molecules which range in size between the very big, excluded from the gel, and the very small can penetrate the pores to varying degrees based on their size. Access to the pores is limited by steric hindrance. If a molecule is smaller than the smallest of the pores in the gel, it will be able to enter the total pore volume.
So some of the advantages of SEC is that we can get relatively short, well-defined retention times. And these narrow bands usually equate to some high sensitivity. We also, there's usually not any sample loss because of no interaction with the stationary phase. And what that means is that imagine if we had a component that was very, very, very polar, had a high affinity for the mobile phase, it could actually elute with the actual elutant, all right? So it could actually leave with the mobile phase component. And so we would never actually be able to detect that component because it would come out with the elutant, all right? And then usually we can use these columns over and over again. One clear disadvantage of using SEC is that we're going to have a tough time being able to detect components that have the same molecular weight. And so if we have proteins that have very, very similar molecular weight, all right, they're going to show up on the same peak or relatively same peak as other components of that or other proteins of that same weight. Next, let's talk about affinity chromatography. So affinity chromatography is one of the most selective types of chromatography employed and often used to separate biomolecules. So it utilizes a specific interaction between one component in our mobile phase and a second molecule that is typically immobilized on the stationary phase. For example, the immobilized molecule may be some antibody that binds to some specific protein. And so when the solute containing a mixture of proteins passes by that stationary phase, only the specific protein will interact with this antibody. And then it binds to the protein, keeping it on to that stationary phase, right? And so then the protein can later be extracted by what we call washing, where we change the ionic strength or the pH of that solvent. Again, it's one of the most specific forms of chromatography. And in biochemistry, some of the interactions that we can often see are things like antigens with antibodies, proteins, antibodies, all right, enzymes with inhibitors, hormones with carriers, or nucleic acids with their complementary or binding proteins.
Separation in affinity chromatography depends upon the reversible adsorption of biomolecules through biospecific interactions on the ligand. Most affinity chromatography experiments are performed in three main stages: equilibration, sample application and wash, and elution. The first step is the equilibration of the stationary phase to the desired start conditions. The second step is sample application and wash. The goal in this step is to bind the target molecules and wash out all unbound material. Non-binding molecules will pass through in the flow-through during washing with binding buffer. In the third step, elution, biomolecules are released from the biospecific ligand into the elution buffer by change in the buffer composition. A common way is to increase pH of the buffer.
Next, we'll look at ion exchange chromatography. Ion exchange chromatography is often used to separate mixtures of inorganic salts, organometallics, amino acids, proteins, and other biological molecules. The mobile phase will be an aqueous buffer at a specific pH carrying molecules with different net charges. And the stationary phase is a polymeric resin matrix that contains large quantities of evenly charged group. An ion exchange chromatography works by taking advantage of molecules' different isoelectric point. And if you remember, this is the point at which a molecule will not migrate in an electric field. And if the stationary phase carries a positive charge, it's called an ion exchange chromatography. And so molecules at their isoelectric point in the mobile phase or have a positive charge pass through first and have little affinity for that stationary phase. And molecules with a negative charge exchange their anions with the stationary phase. And that affinity for the stationary phase depends on that net negative charge of the molecule. If the stationary phase carries a negative charge, it's called a cation exchange chromatography. And so molecules at their isoelectric point in the mobile phase or have a negative charge pass through first and have little affinity for that stationary phase. Molecules with a positive charge exchange their cations with the stationary phase, and that affinity for the stationary phase depends on the net positive charge of the molecule.
Separation in ion exchange chromatography depends upon the reversible adsorption of charged solute molecules to immobilized groups of opposite charge. Most ion exchange experiments are performed in 4 main stages: equilibration, sample application and wash, elution, and regeneration. The first step is the equilibration of the stationary phase to the desired start conditions. When equilibrium is reached, all stationary phase charged groups are associated with exchangeable counterions, such as chloride or sodium. The second step is sample application and wash. The goal in this step is to bind the target molecules and wash out all unbound material. The sample buffer should have the same pH and ionic strength as the starting buffer in order to bind all appropriately charged proteins. In the third step, elution, biomolecules are released from the ion exchanger by a change in the buffer composition. A common way is to increase the ionic strength with sodium chloride or another simple salt in order to desorb the bound proteins. Proteins are desorbed relative to the number of charged groups on their surface. The final step, regeneration, removes all molecules still bound. This ensures that the full capacity of the stationary phase is available for the next run.
And the last type of chromatography for HPLC that we'll talk about will be normal phase and reverse phase. So let's look at these a little bit more closely. So in the normal phase HPLC, the mobile phase is nonpolar or hydrophobic, and the stationary phase is polar or hydrophilic. The stationary phase is the column, which is usually filled with silica beads, all right? And the sample that needs to be separated is added to the mobile nonpolar phase, and as the sample passes through the polar column, those polar compounds will have a high affinity for that stationary phase and will absorb more than the nonpolar compounds, all right? So this means that the nonpolar compounds will travel faster through the column and elute first, and then followed by the polar compounds that are interacting with the stationary phase. In reverse phase HPLC, it's the opposite. The mobile phase is now polar or hydrophilic, right? And the stationary phase is nonpolar or hydrophobic, right? The stationary phase is still silica beads, but has been modified and made nonpolar by adding carbon chains to the silica, right? The sample is added to the mobile polar phase now, and as that sample passes through that nonpolar column, the nonpolar compounds will have a higher affinity for that stationary phase and absorb more than the actual polar compounds, right? And so then those polar compounds are going to travel faster through the column. They're going to elute first, followed by the nonpolar compounds. So no matter what technique we use in chromatography, the final process is to get a readout from the instrument called a chromatogram. And we can tell a lot about a chromatogram and the actual separation of these compounds. And so the position of the peak of a curve in a chromatogram can help us identify what that compound is. And the area under that peak can give us quantitative measures on different things such as mass or the concentration of that compound. So if a detector is placed at the end of the column, the signal from the detector is plotted over time, and the results will be a series of peaks that look similar to what you see in front of you. All right, and the position of those peaks with time is an important clue in identifying the compounds, where those peaks can be compared to known compounds to help identify what it may be. All right. And if a universal type detector is used, such as like a flame ionization detector, the chromatogram may contain hundreds of peaks, like what you see on the right. And while if it's a specific detector, like the sulfur detector, is used, only a few peaks may appear. So from the chromatogram, we can get a few computational measurements here. One of them is the retention time, and so the retention time is the time that required for the sample to travel from the injection port through the column to the detector. And often the first peak is, like I've said before, the solvent, which was used in the mobile phase. It's usually the first thing that hits the detector, but we can see that better in the retention factor. And so the retention factor is equal to the ratio of retention time of the sample compound to the retention time of a non-retained compound. And non-retained compounds uh, may often come off with the mobile phase, and they have no affinity for that station phase and will elute with the solvent at T0 here. And so this is often known as the hold-up time or the dead time. Resolution tells us how the instrument can distinguish between two different compounds. Resolution is calculated using the separation of two peaks and given by the following equation. One rule of thumb is that as resolution increases, so does the time required for the separation. So scientists often have to balance the desire for rugged separation with time and materials. Selectivity is the ability for the instrument to be able to chemically distinguish between sample components. This is usually measured as a ratio of the retention factors of the two peaks in question. Right? And so a high alpha value indicates good separating power and a good separation between the apex of each of the peaks. And so finally, I just wrap everything up here on a table to try to give you guys an overall view of the different types of chromatogram. So we have the types in our first column, the stationary phase used, the mobile phase used, and the type of separation method that we've talked throughout. So I hope you enjoyed this PowerPoint and the videos on chromatography.